There are different steps that can be taken to try and increase the cycle efficiency by recovering as much of the heat as possible, either from the combustion of the fuel in the boiler, or by recycling as much of the heat as possible from the condenser. So we're going to look at both cases. Initially, we'll look at how we can recover the maximum amount of heat energy from the combustion of the fuel in the boiler, and then we're going to go on to look at what's called regenerative feed heating, using feed water heaters. That will then take us up to the end of this teaching pack. So looking at page 18, if the combustion gases from the boiler are being vented into atmosphere at a temperature above that of saturation of the feed water coming into the boiler, then that means that there's energy being needlessly dumped and wasted. So a way to make use of that energy is to add another bank of tubes into the boiler just before the combustion gases leave and go into the chimney. And that bank of tubes is are called economizer tubes. And basically they're just a bank of tubes where the feed water leaving the feed pump are fed through before they're fed into the boiler, and they have the effect of raising the temperature of the feed water closer to saturation, so that less energy is needed in the boiler itself, in raising the steam up to the required temperature for the turbine. So here is a diagram, both a plant diagram and a temperature enthalpy diagram of a system where an economizer is being used. It's very similar, obviously, to, if you look at the diagram, to what we looked at in terms of the reheat cycle. The main difference is in considering the amount of heat that's being transferred into the working fluid in the boiler. Instead of using the enthalpy at exit from the feed pump, i.e. H3 minus H8, when evaluating the amount of heat that's been put into the working fluid up until the superheater, it now becomes H3 minus H9, which is the temperature of the feed water as it leaves the bank of economizer tubes. And that has the effect of increasing again slightly the thermal efficiency. Looking at the TS diagram, the layout is almost identical to that of the reheat cycle we looked at in the last section, with the exception that 0.9 now appears. Now, I haven't located it on the line, but it's going to be somewhere slightly below saturation point here. It really depends on the system. And so that is really the only difference between this and what we looked at before in the reheat cycle. So looking at the equation for the cycle efficiency, as before, it's the network over the heat received, where the network again is the work done by both stages of turbines, high pressure, low pressure. So we have H3 minus H4 plus H5 minus H6 minus the work input to the feed pump, which is H8, sorry, minus H7, and then the heat received is now going to be H3 minus H9, whereas before it would have been H8, plus the heat received in the reheater tubes, which is H5 minus H4. So there's our equation now for the cycle efficiency, where an economizer has been employed. I've also listed here on this page the equation for the actual plant efficiency. Now, cycle efficiency and plant efficiency are two different things. Cycle efficiency simply looks at the amount of heat energy that's been added to the working fluid, the proportion of that has been converted into useful work output. The plant efficiency, however, looks at something slightly different. It looks at the proportion of the fuel, the energy that's available in the fuel that has been converted into and translated into the working fluid. And the way to evaluate the energy in the fluid, in the fuel, sorry, is that equation there, where we have mass flow rate of fuel, so m dot f times CV, where CV is the calorific value of the fuel, the calorific value of the fuel. So that times the mass flow rate of the fuel will give us the amount of energy that's available from the fuel being combusted in the boiler. The net work, or in terms of power, because we've included mass flow rate on the bottom, then we need to do the same on the top, then it's going to be the mass flow rate of the steam times the enthalpy drops in both the superheat up to the point at exit from the superheat section of the boiler, plus the heat received in the reheat section. So the top line represents the energy that's been put into the working fluid, and the bottom line represents the amount of energy that was available from the fuel to put into the working fluid. And the efficiency gives us an indication of how much of that energy from the fuel has actually been converted into energy on the working fluid. If we think about the exchange of energy between the actual flue gases and the feed water, if we assume 100% efficiency, we assume that all of the energy in the flue gases have been the heat loss, if you like, from the energy in the flue gases equals the heat gained by the working fluid, then we get this expression here, where we're employing for the flue gases an equation mc delta T, which we've come across before. In this case, it's the mass flow rate of the flue gases, m dot G, times the heat capacity, specific heat capacity of the flue gases, Cp, times the temperature drop of the flue gases at entry and exit. And that's then equal to the mass flow rate of the steam times the enthalpy change across the economizer. So that gives us an expression of the energy transferred in the economizer. And at the top of the next page, it just reminds us of what the terms mean in our MC delta T equation. So if you consider an example where an economizer is being employed to raise the temperature of the feed water, then example 3 on page 19 says a steam boiler supplies steam at 80 bar 500 degrees Celsius to a two-stage turbine. The steam is expanded first of all in the high pressure turbine to a pressure of 4 bar. It's then reheated to the original temperature of 500 degrees Celsius in a bank of reheater tubes. The steam is then expanded in our second stage in a low pressure turbine down to a condenser pressure of 0.035 bar. And we're given some specification of the system. We have the isentropic efficiency of the two turbine stages. Now you'll notice they're different this time. High pressure turbine is 0.89 and the low pressure turbine is 0.92. The mass flow rate of the fuel is 4,300 kilograms per hour, and the calorific value of the fuel is 42.5 megajoules per kilogram. We're also given the mass flow rate of the steam, which is 50,000 kilograms per hour, and we're told that the feed water temperature at exit from the economizer, which is going to be T9, is 130 degrees Celsius. So ignoring the feed pump work, then we're asked to calculate 1, the power output, 2, the cycle thermal efficiency, and 3, the overall plant efficiency. So going to our entropy chart, we can plot the expansion through both the high pressure and the low pressure turbines. So again, with reference to the diagram in figure 8, using the same notation, number notation, then point 3 represents the input to the high pressure turbine. If we draw our vertical line for isentropic expansion, we're told that the intermediate pressure was 4 bar. So first of all, then point 3 is, we were told, was 80 bar and 500 degrees Celsius, which is equivalent to 8,000 kilonewtons per meter squared. So we have 5, 6, 7, 8, and we also have a temperature of 500 degrees. So when these two intersect, then this is our start point at entry to the high pressure turbine. So if we draw a vertical line until we hit our intermediate pressure of 4 bar, which again is equivalent to 400 on the chart here, then we get 4 dash. That is the ideal condition at exit from the high pressure turbine. Project across to our enthalpy scale, and we have H3 and H4 dash. If we then look at the expansion through the low pressure turbine, then we were told that at 4 bar the temperature was raised back up again to 500 degrees Celsius. So where these two lines intersect, 500 degrees and 4 bar, is our input to the low pressure turbine. If we draw a vertical line down to the condenser pressure, which we're told was 0.035 bar, which is equivalent to 3.5 on our chart here. So we now have the ideal condition at exit from the low pressure turbine. Again, project across from 5 and 6 dash. We're now in a position to be able to evaluate the actual enthalpy at exit from both the high pressure and the low pressure turbines by employing our equations for isentropic efficiency, like we did in previous examples. So if we list our enthalpies then from the chart, and you'll notice just before that I've listed the enthalpy at exit from the economizer, because we were told that it was at a temperature of 130 degrees Celsius. So it's a case of just, in order to evaluate that enthalpy at exit from the economizer, then we just go to our steam tables and locate the temperature 130 degrees Celsius, and then we need to read off the HF value. You'll notice that we don't consider the pressure because 0.9 is slightly to the left of the saturated liquid line. So 130 degrees Celsius from the steam tables, you'll see that HF there is 546 kilojoules per kilogram from the saturated water and steam tables. If we read off our enthalpies from the chart, H3, H4 dash, H5 and H6 dash, then we get these enthalpies here. Of course, H3 and H5 could also have been read from the tables, and you can check that to make sure you're on the right lines in terms of the chart. But then to calculate the actual enthalpy at exit from the first expansion stage, then we've got our equation for efficiency of the high pressure turbine, actual output over ideal, transpose that for actual, and we get 2756, similar to what we did before in the previous examples. If we then apply the same process this time to the low pressure turbine and transpose, and for the actual enthalpy at exit, then H6, then we get 2533. Now the first calculation we need to perform is to find out what the cycle efficiency is, which is going to be the net work divided by the heat received. And here's the equation down here. As before, net work is the work output from the turbine minus the work input to the feed pump, and we were told in the question to ignore the work input to the feed pump. Therefore, we just have the work output from the turbine. So there it is there, high pressure work plus low pressure, divided by the heat received, which is going to be the heat received in the boiler plus the heat received in the reheater tubes. So coming back up here, then we can calculate these four quantities separately. We've got the work done by the high pressure turbine, which is going to be H3 minus H4. In the low pressure turbine, it's H5 minus H6. The heat received in the boiler, and this is again where it's different to what we did before, it's now H3 minus H9 as opposed to H3 minus H8. H9 being the enthalpy of the feed water leaving the economizer, and then finally we have the heat transferred in the reheater tubes, H5 minus H4. Before, sorry, we calculated the cycle efficiency. The question did ask us to find out what the turbine power output is. Now, power P is the same as saying work rate, W dot, where the equation for power and work rate is equal to mass flow rate, and it'll be mass flow to the steam, times the change in enthalpy, so delta H. So to work out then the work output from the turbines, then it's going to be the mass flow to the steam times the combined work outputs from both high pressure and low pressure turbines. So we were told that the mass flow to the steam in the question was 50,000 kilograms per hour. Change that to seconds by dividing by 3,600. And then input our works for high pressure and low pressure turbines, and we get an answer of 22.4 roughly megawatts. Input the values for our cycle efficiency, and we have net work, that is the work output, ignoring the work input to the feed pump, divided by the heat received, and we get a cycle efficiency of 0.48 or 48%. So finally, we're asked to calculate the plant efficiency, which we were told was the network over the heat received by the fuel, or the power divided by the heat received by the fuel. So we're going to be using our 22.38 megawatts for that with the value we calculated in part 1. And then we're going to be using the mass flow rate of the fuel and the calorific value of the fuel to evaluate how much energy was available in the fuel. Just be careful of units here. We were told that the mass flow rate of the fuel was 4,200 kilograms per hour, and we were told that the mass flow rate of the mass flow rate of the fuel is 4,300. I think it said in the question. I've put 4,200 in the solution. You can change that to 4,200 in the question. And the calorific value was 42.5 megajoules per kilogram. So the fact that our work is 22.38 megawatts and the calorific value is 42.5 megajoules, then we can leave them as they are, just as 42.5 and 22.38, because they're both in mega. The only other thing is we need to change, because our mass flow rate of the fuel is 4,200 kilograms per hour, then we need to change our top line also to hours. Watts are joules per second. So to change that to joules per hour, or in this case megajoules per hour, is to multiply the top line by 3,600. You could of course have changed 4,200 to seconds by dividing by 3,600, but you'll get the same answer of 0.45 or 45%.